For the second part of the assignment due this week, you're going to create a new class called Directed Graph. Again, it's using generics, so the idea of the key value pair. Um, and so the whole idea with this is that we have it where we know that we have a key and we have a value, and we have to have a way of being able to, once we have a lot of them, and we want to search saying, okay, I have the key, give me the value. That's kind of where we're going. And so with this, right now we have it where we created an element where we can have one set, one key and one value. But what if we had, 10,000 key values? And I said, for this key, give me the associated value. You got to have some way to go through and search for it and find it. And so that's what we're trying to do. Element is just the basic building block. We finished that. Now we're moving on to directed graph. So a directed graph is where you have it where the edges only go in one direction. This is talked about in other videos, especially the lab graph. So it's different from the lab in that that was an undirected, this is a directed. Remember that a tree is a subset of graphs, meaning that so the graph is kind of the broader type, and a tree is one instance, one specific type of graph, I guess is a good way to put it. So with this, we're going to be able to store generics. So we're not specifying what our key and value are we're not restricting it to a specific type, but we're saying, at runtime we can figure out what we want and have the graph work with it. So the one thing that's important though is that the keys and the values are consistent across the entire graph. So that means that if my key is a string, all keys are strings, and if my values are integers, all values are integers. And so that's what that using element allows us to do, or one of the things that allows us to do. So we're going to use an adjacency matrix just like we did with the graph lab. It's implemented as a 2D array. So this is one of the things that makes this assignment unusual. Typically we just do the kind of linked list type graph. We're talking with pointers. That's what we've learned in class. This is different in that this is a way that graphs are implemented. It's probably not the best fit for this, but if you're able to work through this and figure out how all the pieces go together, I think you'll understand how graphs work, and you'll have a better idea of understanding that there's different ways of implementing a collection. So this is for a graph, which is a generic kind of collection. This is one way to implement it. And there's some applications where it'd be useful to do this adjacency matrix. In this case, it requires you to think a little bit in order to get it to work. So just by convention, the matrix, all the rows, so it's a 2D array, the rows will be the from and the columns will be the to. And so we have a method in undirected graph to print out a representation of the adjacency matrix. It's the same thing with this. You can basically take your code from that and copy and paste it in here. And the rows are the from and the columns are the to. And so you're 0 if there's no link between a node, and 1 if there is a link between it. So the code has to implement the directed graph specification interface. This is just to help make sure it compiles correctly, because if you implement this interface and it compiles, then you shouldn't have any naming problems when I run it on my end. It requires that you have two constructors. So you have a constructor that takes no parameters and creates an initial graph capable of storing 10 graph nodes. So that's the requirement. It's just by default that it sets up so that it can take a size of 10 graph nodes. And there's another constructor that takes one integer parameter, one int parameter, and it'll create an initial graph capable of storing the number of nodes that were passed in as the argument. So for example, if you threw in or initialized it with 100, it would create a graph that's capable of 100. So that means your 2D array would be 100 rows and 100 columns. Also, this is kind of like good programming practice, but just to give you practice with throwing exceptions, if the argument is 0 or less, you're to throw in a legal argument exception. And there's actually a unit test to test that you have that correct. So just to give a simple example to kind of talk through as we're working through the class, let's say this is a really simple graph. So each one of these is a node. These are the edges, and these are directed edges. They go from one to the other. So for example, this one is the key value pair, so it's key A, value 1. This is key B, value 2, key C, value 3. And they have different relationships. So right now we're not talking about trees, we're just talking about a graph. And so with this graph, this doesn't really mean much, but it could. And so what we want to represent this in our directed graph class. So the first thing we have to do is we look and see that the element could be used to represent each one of these nodes. Okay, so that's one piece. The edges we have to represent with our adjacency matrix. Now our adjacency matrix, the only thing we know are an int ID. So we know that because we have, in this case, it could be bigger than this, but we're just saying that right now the size of our adjacency matrix is the same as the number of nodes we have. So the way that the directed graph would work is this side here would be the from, and this side here would be the to. So our rows. And what your code will have to associate each one of these nodes with some type of index. So we could say, for example, that the node associated with A1 is 0, with B is 1, and with C3 is 2. So what I did was I showed that this one's associated with 0, index 1, 0, this is associated with index 1, and this one's associated with index 2. Your code is going to need to make that connection between the element object, which represents a node, and this index, which is how we represent links between the nodes. In this case, from 0 is linked to 2 and to 1. So there's no link between 0 and 0, so that would be assigned at edge of 0. Between 0 and 1 there is a link. That's this one here, so that's a 1. From 0 to 2 there's a link, so that also would be a 1. From 1 there's only a link from 1 to 2, so we put that 1, and these other guys would be 0. So like, for example, a link from 1 to 1 would be that you'd have an arrow coming out and then going back to it. So you can have it where in a graph where an object can have a link to itself. Some graphs that's useful. In this case, it's not. And so for 2, it doesn't have an edge or a link to anyone, so it's all zeros. So this is how we've represented the edges for these nodes. Now you have to have some way of keeping track that this node object's associated with this in ID, and so that's a big part of this assignment. Is you have this integer-based index, and you have these objects, and you need to come up with a way to keep the two together. So you want to know that this 0, when it's referring to here, is associated with this one here, and that 1 is associated with this one. So that's kind of the key challenge with this assignment. And so that's what item D says here. The element class is used to represent each node in the graph. So you're going to have one key value pair for each node. It has to be associated with an index value in the 2D array. And the key value is associated with the data value of the node in the graph. So basically that's just saying what we said previously, is that A is the key, it's associated with the value 1. And so this graph keeps track of that. There is one additional piece, and so this here, I think can get a little bit tricky. So I wouldn't necessarily implement it off the bat. I'd try to get everything else working. You actually can get it to pass the unit test without even doing this. So this would be kind of for the above and beyond piece. Remember, with an index, it has a fixed size. So if you want to add more nodes to your graph than the size of the number of edges there, you have to have it be able to grow. So like an array can't grow, right? But something like an array list can grow. So the idea with this is that you're kind of making a 2D grid that can expand similar to how an array list might. In this case, it's just a simple algorithm. Is once you run out of space, before you add another node, which would cause it to, you have an index out of bounds array, you have to make a bigger array, which is twice the size, and you have to copy from the old array into the new array. So this piece is a little bit trickier. You're certainly capable of doing this. It's just kind of some array manipulation, but you don't need to do this piece to pass the unit test. This is kind of the next step. If you get everything else working, then I would come back and work on this guy. If you're really confused and have no idea how to tackle it, it might be better to just leave it alone. Okay, so now we'll walk through what the different methods that you have to implement. So it's in this directed graph spec. So this is an interface. You just what you do is you just go through and you take this interface and you implement it in your directed graph. So what you want to do is you want to stub out each of these methods. And so the idea with this is you'll get it so that after you stub it out, you can run your unit tests and they'll all fail, but then you can walk through one by one till they pass. So this shows the different ones. This is a directed graph where everything's been stubbed out. And so you'll see here that this is the for creating the directed graph class. This is the syntax for what you'll want to use to implement the generics involved. If you don't entirely understand this, that's okay. It just it's what needs to be in place in order for it to work correctly. And you'll see that with each one of these methods, that it has some, if it's necessary, if it's not void, it has some type of return type. This is enough so now that it'll be able to compile. And so remember, if you have something like a string, something that's object-based, you can return null, and that'll work fine. All right, so the first method you have to implement is this in size. So for this one, it just has to return the maximum number of vertices that the graph can hold. So if we go back to our directed graph stub, this is pretty much the same as what it would be for the undirected. You have to have a 2D array, so you have this. So you're going to have an instance variable in 2D array. I called it edges. You can call it whatever. I don't think that matters for this assignment, so I use the term edges. Here's the two constructors. They're blank. You need to fill in something for both of these, otherwise your code won't work correctly. So you need to initialize edges, but just remember, all this edges is this 2D array. So you have your index of nodes based on an index ID. And so in this case, the size of this is 3, because there's 3 in here. It also happens to be how many vertices there are. However, that doesn't have to be the case. You can have it where the size of the array, or the 2D array, is larger than the number of nodes. For example, this is fine. This shows that it can take up to 5 nodes, even though there's currently only 3 nodes in your graph. So if you were to add a new node, then that would be associated with the next index, which is open. Well, actually, again, it depends on how you want to implement it, but one way you could do it is associate this 3 with the next node that is created. So what this is showing you is that there's a size of 5, but there's only 3 vertices in it. So it has room to grow 2 more nodes before it becomes full. If you were going to add another node, with this assignment, it has it where it can grow if you implement that piece. As I said, you don't need to implement that to pass the unit tests, but you do need that to get, if you want to try to go for 100 on the assignment. So in size tells you the maximum number of vertices the graph can hold. Number of vertices tells you how many vertices are currently in the graph. I'll use the term node and vertice interchangeably in this. It's not to confuse you. Just remember that's pretty common for graphs to be either referred to as nodes or vertices. Those are the common terms, and I interchanged them. But they mean exactly the same thing. This next one is where you have to add a node or a vertex to the graphs. So you're creating a new element of type KV. So this gets specified when you created the directed graph. So K would be, for example, could be like string and integer. It's whatever is specified when you create it. So you create a new element, then you add it to the graph, and it returns the int ID of that vertex in your 2D array. So what that means is, going back to this, let's say this was our current 2D array, which could hold up to 5. There's 3 in there. If it was to create a new node, it would put it in here, and then whatever index you assign to that node, so it'd be either 3 or 4, depending on how you want to implement it. This is up to you. 3 or 4, that's the integer you return. So that outside, so it's returning the integer of what index in your edge matrix that node gets assigned to. This next method returns an array list of all the elements of all the vertices. So you're going to, for example, if you had 3 vertices in there, it would return an array list of those 3 elements. This string adjacency matrix, the string is identical from the undirected graph lab. You can literally just copy and paste your code in there. And you're not even tested on it with this. It's just for you to use for debugging. So you have to have the method in there. Whether or not you choose to implement it is up to you. I think you'll find it helpful for debugging. Add edge. You add, given 2 ints for the indexes, you add an edge between them. And so with this one, it's different than undirected graph. Both those nodes have to already exist before you can add an edge between them. This returns the number of edges given a specific int ID. So for example, if I gave wanted to know all the edges for the node with the int ID 1, if we go across here, there's only 1, and so it would return an array with 2 in it, because that shows that it's pointing from 1 to 2. That's the only one that the only edge it has. For example, if I gave it 0, which is this one, it would return an array of 1 and 2, meaning that it's pointing both to 1 and to 2. This, given the integer ID, it says return the node associated with that, so it gives the element. So in this case, if I was to say, hey, give me the node associated with int 1, it would return this one because we said this one was associated with 1. So it would return an element that has B2 in it. This last one here, what it does is it removes the node or the vertex with that int from the graph, and it wipes out any edges. So going back to this example, let's say we were to delete node 0, which is this one, A1. So we'd remove it from the graph, and what we'd do is we'd still leave this spot open in the adjacency matrix. We just wipe out all the edges, so these 2 would get turned to 0. And also, if there was anything pointing to 0, and so that would be this column. If there was a 1 in here, that would get wiped out also. So these would go to 0, these would go to 0. That clears out all the edges. And the other thing it does is it returns the actual element associated with that. So in this case, if it was given an index of 0, it would return this. So this might sound, hopefully this video helped clarify the different parts of the graph. This is a way of implementing graphs that is slightly complicated, so you're going to have to spend some time just trying to figure out how these different pieces go together. And so in your implementation, as you're filling out these different methods, which we'll go through in the next video, we'll spend some time on, This isn't the only instance variable you need. You need some other, at least one, maybe more, in order to keep track of your um, the actual elements that represent nodes. So you need to have elements, and somehow you have to map those elements to their indexes. So you have to know that, hey, I'm element A1 and I'm associated with index 0. So that's something that you'll have to think about. How can I, what's the best way to do that? And come up with and so this is where we're really getting into implementation. We have to implement the details to put this spec together.